me record the session. First of all, before I start my today's session, just reply me that you can see my whiteboard. Let me ensure that. Participate. Yes, okay. Thank you so much. Now, see, in the last class, we discussed about Poisson distribution. And to start with, let me give the formula or probability mass function for the Poisson distribution so that it remains in front of us. So Poisson distribution, I'm not going to write the entire definition, don't worry. Formula was this: probability of x equal to small x, e to the power minus lambda, lambda to the power x by x factorial. This is the formula of the probability function. And also I wrote that lambda is actually a kind of quantity which is obtained by multiplying number of experiment by probability of success, and probability of Poisson distribution can be re-expressed in the following form, which is e to the power minus np to the power x by x factorial. Okay, but let me now demarcate a line between these two expressions. Okay, let me demarcate the line. I am coming to this particular point later on. This particular expression is a special type, but I'm going to come to this particular point later. But first of all, let me discuss about something of this formula. And I told you in my last class that in Poisson distribution, the parameter is the quantity lambda. Parameter is the quantity lambda. Okay, so if you know lambda somehow if you know lambda, then you will be able to identify the probability for various outcomes. In my previous class, we talked about the coin tossing problem. Coin tossing problem is my benchmark problem, which I kept on dissecting one after another in various ways. I found expectation, I found variance, I dissected the problem, I found probability law. The probability law satisfies directly corresponds to binomial probability law. And I somehow, because the parameters were known, I tried to calculate the probability with the help of the Poisson law also. And I told you that we got two different results by applying binomial probability and Poisson probability. And I said that it is a matter of thinking whether we can indeed apply Poisson probability distribution to the system or not. Now, the punchline is that, and I also replied you that the system of coin tossing is actually not eligible for applying Poisson probability distributions formula over there. We cannot apply this formula to the given problem of coin tossing. Now, what is the matter? Why can't I do so? Because there was not much difference between the probability. One was coming as 0.27, another was coming as 0.25. People have varied opinions about this. Some people may think that it is not a matter of concern. 0.27, 0.25, okay, we can manage it. But if you are really doing statistics and if you are really concerned about what probability distributions you are applying, then it is a matter of concern. 0.27 to a statistician, 0.27, 0.25, they are not same thing. Otherwise, you couldn't have calculated the probability at all. When you are giving the probabilistic interpretation of the system, that means you have to consider what value is coming. Okay, you cannot neglect it. This is the ethics that you must follow over here. But why? The question is, why can't we apply probability, Poisson probability law in the given problem of coin tossing? Or to put it in other words, what is the criteria? What is the criteria on the basis of which we are eligible to apply Poisson probability law? The answer lies in the fact that probably we have missed yesterday, but I wrote it in the formula. When I wrote the expression of the Poisson formula, which is given by this, beside this expression, I also wrote, there is no space, so I'm writing over here. Beside this expression, I also wrote that the x is taking the value from 0, 1, 2, and it keeps on going. Whereas for binomial distribution, binomial probability law, which I'm writing over here, ncx p to the power x, q to the power n minus x, my x was taking the value 0, 1, 2, up to n. What is the difference between these two terms? This is the important part that you shouldn't neglect. See, this immediately we can say that these values are finite. Okay, x can take value from 0 up to total number of experiment. And here, the possibilities of x are infinite. If I say the possibilities of x are infinite and it has no upper bound, that means this quantity n, the number of experiment, which was bounding the limits for the values of binomial case, is actually missing. So question is isn't there any bound? Isn't there any bound on how many times must we do the experiment? Must we do the experiment? Is the n missing? Okay, don't we know the count of n? Okay, but if it is so, how did we calculate n over here? How did you put n over here? I will come to this particular point later on. Keep it in mind that I have to give a reply to this particular setting. But from this particular expression that x is taking value from 0 to up to infinity, it is a matter of question that what is the value for n that we must choose. Now the answer to this question, I must reply that there is no bound of observing things in case of Possion probability law. I do not know how many times I must do the experiment to get a success. It is not known to me. Say, for example, suppose a COVID-19 like virus has come again into our society and is affecting people. Say, for example, Ebola virus, whose vaccine is not available. Now, this Ebola virus is affecting people which is a zoonotic virus, and it has come directly from the bat to human. Probably you have heard about Ebola, and it was creating havoc in the in Sierra Leone. Somehow it was contained, but COVID-19 was not contained. There are other mysteries, other conspiracy theories, but I'm not going into the details. It is not a matter of discussion now. But suppose Ebola, it is this virus, this reproduction is actually creating havoc. People are getting affected. It's a deadly virus. People are dying. And you have, by seeing the nature of the virus, you have prepared a vaccine. And you are putting the vaccine, you have started vaccinating the people of the affected region in the hope that they will show the sign of recovery. Now, you have seen that when you put the first dose of the vaccine to the patient is not recovering any sign. Is not showing any sign of recovery. He is getting worse and worse. So you have modified the vaccine. You are again pushing to a group of people. No recovery. You are again refining your vaccine, pushing to a community. No recovery. Again, you are pushing it. After some time, no recovery. Again, after 6 months, you are pushing it after some little bit of modification to the vaccine. No recovery. In this manner, now it has become a headache for you, and you are thinking that how many times must we modify the vaccine and push it to the community to get the first success that a person is responding positively. We never know. This situation, in this particular situation, you never know that how many times you are supposed to do the experiment. Okay, but after many times of doing the experiment, after many observations, this word many is actually very confusing word. This many can be 6 months, this many can be 1 year, this many can be 1 month also. This many doesn't mean that it is, whenever I'm saying that the number of experiment is many or infinitely many, that doesn't mean that they are infinite. I have to do the experiment infinitely many times, because human lifetime is not infinite, it is finite. So in a finite lifetime, you cannot perform infinite number of experiments. How can this be possible? In no statistics book it is explained. I have seen many teachers that they don't explain this particular thing. But let me tell you, here by infinite, we actually mean, I'm not sure. Infinite means I'm not sure how many times must we perform the experiment to get a first probabilities of success. I do not know what is the value, what value should be put in place of n to get the first probability of success. Theoretically, mathematical language, this particular sentence that I'm uttering, it is called infinite. I am not sure. And therefore, in this particular n for this vaccination problem can be of this number of observations can be 1 month. After 1 month, you can get a first probability of success. It can be 2 months, it can be 6 months, it can be 1 year or 365 days. It can be 5 years. It can no limit at all. Okay, to get a first probability of success. First success is here in this particular situation. The success is affected people is responding to the vaccine. Now, in COVID-19 case, that what is happening? Vaccines have been prepared. Covaxin is there. Covishield is there. I am co-vaccinated. You are Covishield vaccinated. Somebody is taking Sputnik, Pfizer. Many vaccines are there, but we do not know whether these vaccines are effective or not. It is just a kind of, elusive thing that, yeah, okay, probably I am safe and secure. But I do not know. I do not know whether if indeed the COVID affects me, whether it will work or not. Many research papers are coming, but nobody, no such research paper is actually was able to predict the probability distribution of the COVID-19 virus. And since the actual probability distribution hasn't been established, so we cannot predict the nature of the COVID-19 virus. Okay, so probability distribution of this particular virus, its community is missing. Anyways, I shouldn't divert from the topic, and let's come back to our Poisson distribution case. So we are not sure about how many times must we perform the experiments, and that we actually call as infinite. Okay, so in this situation, so there is a condition, underlying condition, on the basis of which you can apply the Poisson probability law, not always. So what are these conditions? The conditions are, there are two conditions. First of all, I am not sure. Okay, I'm uttering the word in sentences, but I'm writing it mathematically so that you can correlate the things. First condition number one is, I am not sure how many times must I perform the experiments given by point number. Point number two is that during this process, the probability of success, which I can denote by small p, is very low, corresponding to the in comparison to the number of experiments that I have performed. You are vaccinating people for 1 year, one people is responding. So your small n, do not count this small n to be 1. Okay, do not think that the year is 1 and the people responding is 1. That is not Poisson. Remember, if you count it in this manner, 1 year, 1 response, that is not the thing. Okay, do not correlate like this. You have to understand this particular fact. 1 year, you consider this to be 365 days. So your number of experiment is 365, because when you are pushing the vaccine, you are monitoring the person. Each time you are pushing the vaccine, you are monitoring the person. So every day counts. Year wise it is not, because I have to change the thinking of my observation. Na? This discussion that I'm making, it is very important. I can't just give you the formula and give you some problems and ask that you, okay, these problems are done in this particular manner. No, this is not the case. You have to feel the intricacies before you apply something. So 1 year means, how can I put my number of experiments? I am actually trying to establish a probability distribution, or I want to check the model of Possion distribution to the given system. So I have to understand how to extract out, how to consider my number of experiment. Number of experiment means you feel the situation, pushing the vaccine, and you are monitoring the person. Not each day, I must say that each hour is counting. It could have been like this. The person can respond at any hour. So 365 days multiplied by, I mean, 1 day is 24 hours. So 365 days into 24 hours can be your experiment also. 365 days, 365 into 24 hours. I think this would be the appropriate uh, value for the number of experiment to be performed in this particular case. Corresponding to that, if you find that only one person is showing sign of recovery, obviously you will automatically say that, okay, then in that particular case, small n is very large, mathematically infinity. How can I express the word very large other than to consider to be n tending to infinity? I'm not writing n equals to infinity, because infinity is an abstract concept. It is not a value. Equality sign cannot be put. Corresponding to the number of experiment, large number of experiment, my probability success is very low. Only one people have responded. It's very poor. So it is very poor. We are putting it as probability is tending towards 0. So in observation, so number of observation is increasing in increasing direction. Probability of success is in decreasing direction. So this is the, I mean, direction of movement of number of experiment, and this is the direction of movement of number of probability of success. In this situation, so these are the two conditions. Third condition is also very important. Third condition is saying that try to do the kind of thing, or try to manipulate the thing, although it is not in your hand, but try to find out whether, after getting this number of experiment and the first probability of success, calculate the quantity NP and see whether this quantity is a finite quantity or not. If it is a finite number, it is not infinity, then you can, that is I mean, required actually. And this finite quantity, this NP, is actually denoted by some notation. This notation that I'm using is called the lambda. So you see, these are the three conditions on the basis of which I can apply Poisson probability law to a given system. Okay, but not always. But what is happening on the right hand side? Here I have got a finite n. Here my n was finite. It was having the value 4. It is finite. Probability of success is also not very poor. Probability of success is half, and NP was 2. Obviously, NP is a finite quantity. So how can we apply? Why not how, but why can we apply this particular thing to the given problem? Okay, is it absolutely wrong to apply this? First, I can answer to this question in two different ways. First of all, yeah, it was not appropriate to apply binomial, you apply Poisson law to the point tossing problem. It was not appropriate because the situation doesn't demand, and it is not fulfilling the criteria of Poisson distribution. Number two, one important fact is that this formula of binomial probability ncx p to the power x q to the power n minus x tends to e to the power minus lambda to the power x by x factorial. This quantity tends to this under the condition n tending to infinity, p tending to 0. It's a very important theorem, but I'm not going to deduce the theorem, because otherwise, if I start deducing the theorem, you will lose interest. In the engineering mathematics, we are only concerned about the applications, not the deductions. This particular theorem, I'm putting it a star mark over here. Any interested student can go through a book to get it, how it is actually coming. But it is a matter of those people, it is a study of those people who are actually pursuing higher maths, MSc or kind of thing. Okay. So it is not matter of, it is a kind of thing that I'm not going to discuss. But remember, under these two conditions, this binomial probability is actually tends to follow this kind of expression, and this can be proved. I have the proof with me, so if you want, I can later send it to you, the image. So what we did over here is actually called Poisson approximation. Poisson approximation to the binomial case. To the binomial case. This is what I did. Poisson approximation to the binomial case, keeping in mind this particular point. I was somehow able to apply this Poisson law, but practical sense, I did it wrong. This is, we need to keep in mind. Practically, we are wrong. We are not eligible. Anybody can do anything by forcefully. And definitely the values will come. Those values will be treated as a garbage value. So 0.27 that the value was coming is actually a garbage value. So before we apply the Poisson law, you have to understand the situation. Is it satisfying the conditions of the problem? Okay. If it's satisfying the conditions of the problem, then okay, fine. We are, if it is satisfying the conditions of the probability Poisson distribution, then we are able to apply the Poisson distribution. Otherwise not. Okay. So the interesting part is that only finding the parameters, that parameters are present, so we are eligible to apply the probability. It is not counting actually. You probably were thinking that, sir, yes, previously told that parameters can tell us that, yeah, okay, so you have got this probability distribution, so you can calculate. Not only the parameters, certain cases are there where not only parameters, but the situation also demands whether this probability law can be applied or not. Okay, now to establish this fact, let us consider the problem which is given as follows. I'm taking this particular point from the book, problem from the book for which I actually shared with you. So it is given as follows. Suppose the average number of accidents, suppose the average number of accidents occurring weekly on a particular day, on a particular day on a, sorry, not on a particular day, particular highway, okay, is equal to 1.2. Approximate the probability that there is at least one accident this week. Very simple problem, but very significant one. First of all, the author of the book he has not mentioned whether this particular problem, what binomial, what probability Poisson distribution you must follow over here. Although I have taken the problem from a chapter of Poisson distribution, so the chapter is telling me, yeah, it is from the chapter of Poisson distribution, then it has to be a Poisson distribution. This is not a mathematical thinking, isn't it? So how to analyze this situation, whether it is indeed the Poisson law, it is indeed the Poisson distribution or not, you have to dissect the problem and you have to find it out. First of all, you see that one important point, that it is saying that average number of accidents is 1.2. In the coin tossing problem, we had the value for small n, number of experiment, and probability of success, and we multiplied n by p. So we found the value, but here the value of n is missing, the value of p is missing, but this quantity is given, which is 1.2. Obviously, we can understand that we have to apply this particular value somewhere, somehow. Second is that, unfortunately, here the success, if you want to define the success over here, here the success is, how to define the success? Here the success is accident, when accident occurs. When accident occurs, this is the success. Now, don't be sad. How can an accident be a success? How can this be a success? Okay, so you have to analyze. Are we the people happy when the accident occurs? No, this is not the case. Accident occurs, it is a success, is because you want to prove that the area on the highway where the cars are passing, the trucks, lorries are passing, this area is accident prone zone. And to prove this, you want to put a signboard over there, and you have to, satisfy the government authorities or municipal authorities that, yeah, you are doing the experiment, and next time they must put a sign over there that it is an accident prone zone. Often you have seen this kind of signs in the highways where the signboards are actually placed, but suddenly they just in some highways there is a kind of turn which is called blind turn. Okay, so these blind turns are not a matter of, you don't have to perform any experiment over here. Blind turns are always accident prone, and you have to be very careful if there is a blind turn. It often happens in hilly regions, but in plain areas also, some parts of, you will see that it is considered to be the accident prone zone. How? Because you cannot see that, you will not be able to see any blind turn over there, but it is accident prone. Some road construction, some defects on the road construction are there, which the engineers can only understand, and they have observed this particular portion for many times, and they have come to the conclusion. So if accident occurs, and if we consider this to be the success, it means that we want to put a signboard to inform people about, to be careful. Okay, now theoretically it can be established that the mean of the Poisson variate, is actually lambda. Not only this, the variance of the Poisson variate is also lambda. Variance of Poisson variate is also lambda. Theoretically, it can be proved. Now, this proof I'm going to show you in module 4 of your syllabus. So you have to wait to get this particular proof. Not right now. Not every proof is not beyond the scope of the syllabus. This proof I'm going to show later on, when doing the module 4. So if it is so, then obviously for this particular problem, I have got my parameter, which is 1.2. Okay, so lambda is known, and I say that since lambda is known, the parameter is known, so Poisson probability law can easily be applied. But it is not always that the highway is accident. I do not know what is the nature of the highway. I want to put a signboard. I feel that this particular area is accident prone, but I have to establish the fact. And to establish the fact, I do not know how many times I have to perform the experiment. So for how many days I have to keep observing whether accident occurs or not. So that is not known to me. So obviously here in this particular scenario, I can consider n to be infinity and p to be very small, because I will hope that accident shouldn't occur. Okay, I keep on increasing the number of observations, but accident is not occurring. Very poor probability of success. I hope that. So this particular situation is actually following the Poisson distribution. So this follows the Poisson distribution, and we are able to find out the probability using the Poisson distribution formula. Obviously, this particular problem doesn't follow binomial distribution because small n and small p are missing. So obviously, binomial distribution's chance is eradicated. Now to find out now our job is to approximate the probability that there is at least one accident. So we can write it in the following manner: probability that there is at least one accident can be mathematically expressed as probability of x greater than 0. Okay, x is strictly positive. What is x? You have to define the random variable. X is number of experiment and number of accidents. This is my random variable here, number of accidents. And since it is following the Poisson distribution, so we can write the probability of small x accidents in the following manner: e to the power minus lambda, lambda to the power x by x factorial, where x is taking value 0, 1 to up to infinity. Now you may think that, okay, my God, probability of x is greater than 0. Shall I have to put all the possible values and calculate the infinite series to calculate this probability? The answer is no. Here, this particular formula will come to rescue you from this headache. Probability of a bar is equal to 1 minus pa. This axiomatic approach, if you consider this is not an axiom, this is a theorem, but we establish this particular theorem from axiomatic approach. So this is coming to you for your rescue. Okay, it is saying that no, you don't have to perform any sort of infinite series type of operations, clumsy operations. You can apply this particular fundamental law to the given problem to find out the probability. So why? Because we know that complementary event to this particular problem, the complementary event to this particular problem is of this particular situation, that is x greater than 0. If it is my event capital A, then its complementary event a bar will be x equal to 0, because x cannot take values lesser than 0, because x is a number. Negative numbers cannot occur, na? So how many times the accident is occurring? -1 times accident is occurring. You cannot say this. So if x greater than 0 is my a, then x equal to 0 is my a bar. So you can write this probability of x greater than 0 as 1 minus probability of x equal to 0. Very easily you can do this, and then you can put 0 in this particular formula. So we are going to write it as e to the power minus lambda, lambda to the power 0 by 0 factorial. And as lambda is 1.2, here our lambda is 1.2, because you already know that lambda gives you the average number. So it is 1.2. So we can put e to the power minus 1.2, and that will be subtracted from 1. And let's calculate this probability quickly. This probability, even if you keep it in this particular form, then there is the problem with this. How you are the application will also only be how you are, whether you are able to judge the situation and apply Poisson probability law, that will be judged. Okay, no, not the value will not be judged. Anyways, the value is coming to be 69.6988. One more thing I must say to you, that whenever you will be doing statistical calculation, it is a kind of it's not a universal statement. It is a statement. It is my statement. I always tell to the students that whenever you will be doing this kind of statistical calculations, always keep 4 digits after decimal points. Okay, 4 digits. It is justifiable. One day I will tell you the story why I actually prefer to keep 4 digits after decimal points. Even if you you are getting the value like 0.25, keep it a habit to write it as 0.2500. So this will always be in your mind that I have to keep 4 digits after decimal points. It is a I mean a good practice that you all must follow. Now I hope that in this particular class, 1 or 2 problems I can discuss at least. So if you want, you can please join in the next session. Next session will be very short. I will discuss 1 or 2 problems, and then I will end my today's session. So I'm stopping here right now. Please join for at least 15 minutes in the next session. Okay, if you're really liking the session.